In this video, we're going to be talking about the Chinese remainder theorem and solving linear congruences and how they can be used to solve some tricky problems like this one here very easily. Okay, let's start off. So what is the Chinese remainder theorem? If a positive number x satisfies these modular conditions, let's say x is equal to a1 mod n1, x is equal to a2 mod n2, so on. Basically, what the Chinese remainder theorem is saying is that as long as all of these numbers are relatively prime to each other, then if all these numbers are relatively prime to each other, then there's always going to be exactly one unique solution mod the product of all these numbers. So for example, if we have something like 5 mod 8, 6 mod 7, and 2 mod 5. And we're trying to find a solution mod something. Mod, well, the Chinese remainder theorem guarantees exactly one solution. It guarantees one solution, mod 5 times 7 times 8. And this one, well, the Chinese remainder theorem does not tell us how to calculate the solution, but it tells us that there has to be one solution and there can't be more than one. Okay, so another key thing here is that it won't work if these numbers aren't relatively prime. So for example, what if this was 2 mod 4? Well, now in this case, there are no solutions because the number can't be 2 mod 4 and 5 mod 8 at the same time. Sometimes on the other hand, it could have a solution still, like 3 mod, or maybe like 1 mod 4, and it would still have a solution. But the key thing to note here is the Chinese remainder theorem only applies if all of the values the mod bases are all relatively prime. So all of these bases, they all have to be relatively prime, as you can see there. Because if they share any factors, then there's a chance we might not have any solutions. So the Chinese remainder theorem is kind of limited in a way. It only tells us that there is a solution. It doesn't tell us how to find the solution. But there is another method to find the solutions. In fact, there's more than one. The first one, guess and check. Yes. Like we could just guess and check a bunch of numbers by looking at all the values of mods until we get an answer. Okay, so this is the cool method, and this is, in my opinion, the best method, the algebraic method. So the trick is you find two congruences. N is R1 mod M1, R2 mod M2. So what you want to do is you want to rewrite them algebraically. So we write n equals k times m1 plus r1. And n equals j m2 plus r2. So basically what this is that we're rewriting the mod condition algebraically. And the reason this is true is because if a number is r1 mod m1, then it's just many multiples of m1 plus r1. Similarly, we have here. So the thing here is that these are equal because these numbers have to be equal, right? So the thing is, what you want to do is you want to set them equal to the mod of the smaller value. So in this case, let's say m2 is smaller. You set them equal and you get this. And what you would do is now subtract r1 to get r2 minus r1. And then what you do is you multiply by the modular inverse to both sides. Now this might seem a little confusing, so let's just take a simple example that uses this technique. Find the smallest positive integer greater than 100 that leaves a remainder of 5 when divided by 9 and leaves a remainder of 4 when divided by 17. So what is that in terms of mods? Let's say x is 5 mod 9 and x is also 4 mod 17. So what do we do with these mod conditions over here? The first step, we write them algebraically, and that's what we're about to do. The first condition algebraically is something like 9a plus 5, right? Because 9 times 9, it's a multiple of 9 plus 5. So 9 times anything plus 5. The second condition algebraically is something like 17b plus 4, right? So now what we do is we set these terms equal mod 9. So what is that? That means we have 9a plus 5, or rather, we don't even need to do that. all we can say is that 17b plus 4 has to be 5 mod 9 as well. Because if x is 17b plus 4 and x is 5 mod 9, then 17b plus 4 must be 5 mod 9 as well. So let's write what this means here. 17b plus 4 is 5 mod 9. And let's subtract 4 from both sides. And now the key thing to note here is 17 is just negative 1 mod 9. So this is going to be times negative 1b. And from here, well, what is b mod 9? B has to be negative 1 mod 9, right? Because negative 1 times negative 1 is 1. Now that's actually kind of cool. Usually it won't be this simple. You might have to do a little bit of guess and check, but the guess and check here is much simpler than anything you'd have to do if you were to try to do these manually, because it's mod 9 instead of mod 17 and mod 9. So it's much easier to guess and check. And it's much smaller and it'll take you much less time. But in this case, we got lucky. We don't even need to guess and check at all. You can easily see b is negative 1 mod 9. So what is this algebraically? Well, if something is negative 1 mod 9, it can also be expressed in the form 9c minus 1. So b is 9c minus 1. This becomes 17 times 9c minus 1 plus 4. That's x. Let's expand this out. 17 times 9 is 153. So 153c minus 17 plus 4 equals 153c minus 13. So what does that mean? That means that the number must be 140 mod 153. And the good part here is that we can easily check if our values actually work. 140 is clearly 5 mod 9 and 4 mod 17. So we're good. It does work. So that's essentially, and the reason we can convert it back from the algebraic form to the mod form. And that's essentially the process. So there's actually a third, so yeah, from here and then we just guess and check. And then we convert back to mods. So now here's an actual formula, and it's a little hard to memorize. I'll be honest, I haven't memorized this myself, but if you want to, you can. N is just R1 plus M1 times the difference R2 and R1 times the modular inverse of M1. And it's basically derived from the process we just went through. And you can do this if you want, but you can really just use the algebraic method. That works perfectly fine. But this might save you a little bit of time. Okay, next off, let's take a look at an example from the AMC. The positive integers n and n squared both end in the same sequence of digits, a, b, c, d, when written in base 10, where the digit a is not 0. Find the 3-digit number a, b, c. How do we do this problem? Because first of all, we know that n must be equal to n squared mod 1000. Right? So we're asked to find the positive integer, and you're given that these both end in the same sequence of four digits when written in base 10. So they would actually be equal mod 10,000 because the last 4 digits are all the same. And we're just asked to find the first part of this number. So essentially what we have to do is find what this is that allows them to be equivalent mod 10,000, not 1,000. So we can rewrite this as n squared minus n is 0 mod 10,000. And this simplifies to n times n minus 1 is 0 mod 10,000. So this right here has to be a multiple of 10,000. Well, first of all, clearly we know 10,000 is 2 to the 4 times 5 to the 4, right? So now we essentially kind of have a few possibilities here. The first possibility is that either n or n minus 1 is 0 mod 10,000. So basically what that means, there's two possibilities here in this case. If n is a multiple of 10,000, then n is 0 mod 10,000. If n is n minus 1 is 0 mod 10,000, then n is 1 mod 10,000. That's one case, but the key thing here is that none of them work because a cannot be 0. And 0, I mean, if n is 0 mod 10,000, then the last 4 digits are just 0, 0, 0, 0. In this case, it's 0, 0, 0, 1. Both of them have a being 0, so you can cross out these cases. They don't work. So now the other cases is that maybe n is a multiple of maybe 2 to the 4, and n minus 1 a multiple of 5 to the 4. Or flipped. So essentially, what does that mean? Is it possible maybe to have some factors of 2 here, maybe 2 cubed, and another factor of 2 here? Well, the trick is their product is a multiple of 2 to the 4. So if their product is a multiple of 2 to the 4, then if we split the factors between n and n minus 1, is that even possible? Well, n is different mod 2 than n minus 1. N is never going to be equal to n minus 1 mod 2, which means that if n is even, then n minus 1 is odd. If n minus 1 is even, then n is odd. So that means that we cannot split the factors of 2, because then now we have 2 even numbers as n and n minus 1. That's not possible though. So therefore, all the factors of 2 to the 4 must be on one number. Now what about 5 to the 4? The same thing actually is true. The same logic we can apply. The logic is that because 5 to the 4, we can, again, if you split the factors here, we can't have something like 5, 5, and 5 cubed. Because these values aren't the same mod 5. These values are not the same mod 5, so they both can't be multiples of 5. You can't have a multiple of 5 consecutive to another multiple of 5. So all the powers of 5 must be on another number. So now from here we essentially kind of can break it down further into two cases. So the two cases are case 1. Case 1 is n is a multiple of 16. So n is a mult of 16. And let me write this in mod. I don't know why it went this way. N is congruent to 0 mod 16. So n has all the powers of 2. And now we're saying we already counted the case where n also is a multiple of 5 to the 4. Like that was the case where n is just 0 mod 10,000. Because then n is a multiple of both 2 to the 4 and 5 to the 4. We already counted that case. We know it doesn't work. So we're going to look at the other cases. So n is 0 mod 16. And then n minus 1 will be 0 mod 5 to the 4, which is 625. Right? Case 2, it's the opposite. N minus 1 is 0 mod 16. So n minus 1 is 0 mod 16, and n is 0 mod 625. And we already counted for the cases where one number is both a multiple of 6, where one of n or n minus 1 is a multiple of 16 and 625 in the cases over there. And we found that they both don't work. So now essentially, the only thing that we have left to do is solve these congruences. Let's first rewrite this. N 1 mod 16. This one is n 1 mod 625, 0 mod 16. So now, how do we solve these congruences? Guessing and checking would take a long time. We use our trick. Well, the Chinese remainder theorem guarantees a solution to both of these equations. So they both must have a solution. Let's see what those solutions are. So case 1, let's solve that one first. Case 1, we'll do it over here. N is 0 mod 16, and this can be rewritten as 625a plus 1, right? In our algebraic form. Right? 625a plus 1. So 625a plus 1 is 0 mod 16. So 625a plus 1 is 0 mod 16. And from here we know that 625 is 1 mod, or 65 is 640 minus 15. And the key thing to know here is 640 is a multiple of 16, 0 mod 16, and 15 is negative 1 mod 16. So it's just going to be minus negative 1 mod 16, which is just 1, minus negative 1, which becomes 1 mod 16. So it's just 1 times a plus 1 is 0 mod 16. Isn't that so neat? So now we have a is 15 mod 16. That's cool, isn't it? So now let's plug that in over there to our 625a plus 1. You know a is 15 mod 16. So let's rewrite this algebraically. 625 times, well, 15 mod 16, we can also write it as, we can also rewrite this as 16c plus 15. So 625 times 16c plus 15 plus 1. Okay, so that is the expression over there that we're looking for. This is the expression we're looking for that will represent the solution to that mod equation. So if we expand that out, we get 625 times 16c plus 625 times 15 plus 1. And this is just the mod. This is just going to be 10,000c. So this is going to represent the last 4 digits. And we can multiply that out. That's 6250, 625 times 10, plus 625 times 5, which is 3125. We add them up, we get 9375 plus 1, 9376. Those represent the last 4 digits. Now let's solve this one over here. We do this very similarly. It's literally the same process, in fact. Let's say this is 625b. So 625b is 1 mod 16. 625, like we found earlier, is just 1 mod 16. So b is 1 mod 16. Isn't that cool? B is 1 mod 16. We plug that in. 625 times, let's say some d this time. So let's say 16d plus 1. 65 times 16d plus 1 is 10,000d plus 625. So in case 1, the last 4 digits are 9376. In case 2, the last 4 digits are simply 625 with a 0 in front. So therefore, the second case doesn't work because a is not supposed to be 0. In this case, a is 0. So therefore, these are the last 4 digits, and ABC is just the first 3, 9, 3, 7. So this was a long problem, so let's summarize. First, we started off with this condition here. Then we simplified it to this, and we saw that the cases where n or n minus 1 is a multiple of 10,000 don't work. And then we split it up into 2 cases because we know a number must be a multiple of 2 to the 4 and 5 to the 4. So we found one set of congruences here because in this case we had n is a multiple of 16 and n is minus 1 is a multiple of 625. And over here we had n is 1 mod 16 and 0 mod 625. And we solved them using our standard method. And then we found that only this one here worked. Gives us an answer of 937. Now, by the way, there are many modular arithmetic practice problems you can find in the free Mastering AMC 1012 book. The link will be down in this description. You can click on it and get it completely for free. Next, we're going to talk about diophantine equations. So diophantine equations are really cool. They're basically like an equation, except now we've got an integer condition as well. You often have to use number theory techniques. That algebraic number theory content we'll be discussing in the next video, click on it right there.